Hey guys, so today we're going to do intermolecular forces. I know we talked some about them last time, but today is really the day we're focusing on them. Remember, to do intermolecular forces, I need you to be able to draw the structures, which means you're going to need to have your periodic table out. So also remember, I will call intermolecular forces IMFs. Okay, so the strength is what determines the state. We already talked about that. Also, the strong molecular forces are liquids and solids. Again, we already talked about that. And the weak intermolecular forces are going to be gases. So, the first type of intermolecular force, it is present in all molecules, all atoms, every single thing you can think of. It has these dispersion forces, which are also called London dispersion forces, but generally I refer to these as LDFs because, again, it's kind of long, so we just abbreviate. Okay, so it's found in everything, every single atom, every single molecule. So what happens in these, and you don't really need to know this so much, but obviously electrons are always moving. You can see them moving, and then at some point they all kind of just move to one side of an atom or a molecule. When this happens, it creates these partial charges. Remember, we saw these in chapter 10, and they kind of make all of the other atoms or elements or molecules in the compound, in the element, they make them all do that, so they all have an instantaneous spot where they have partial charges. That's what an instantaneous dipole is. So that fleeting separation is called either an instantaneous dipole or a temporary dipole. Now, we did discover these in the 1900s. Remember, we didn't know about electrons for a while in the 1900s. Okay, so here it's showing once one does it, they all kind of do it, and then they move back, and they're not doing their instantaneous dipole anymore. All right, so the magnitude of the dispersion force is dependent on the number of electrons, or how easily they move around. Okay, what is most important here is that the more electrons they have, the more polarizable it is, so then the stronger the LDF. So I'm going to write up here, and this is really what you need to write. So more mass means that there's more electrons, because generally electrons and protons are equal. That means it is more polarizable. And polarize means like to create poles in the atom, like partial positive, partial negative. And then it means it has a stronger LDF. So that is kind of what all of this red is saying. The more mass it has, the more electrons it has, the more polarizable the atom or molecule is, and the stronger the LDFs are. I will tell you, on the test or quiz, I will be looking for the word polarize if I ask you why. So it is important that you write this on your periodic table. So here are some examples as mass increases. These are all noble gases. The boiling point also increases. Just remember that stronger IMFs equal higher boiling point and higher melting point, MP. Okay. And these are in Kelvin. So even though these are noble gases, they seem large, but they're really very low when it comes to Celsius values. All right, so which halogen has a higher boiling point? So obviously that's going to be iodine. Because iodine has more mass, so it's more polarizable, so it has stronger LDFs. Okay, it has a lot more mass, but if it has more mass, you can compare them. CH4 or C2H6. C2H6 has more mass, 30, versus the 16 that CH4 has. So C2H6 or ethane will be the one that has the higher boiling point because it's more polarizable. Okay, we use the terms more polarizable when we're talking about the same intermolecular force. So again, the first IMF is LDFs or London dispersion forces. Intermolecular force number 2 exists in all polar molecules. So this is why it was important in chapter 10 that we learned about polarities of molecules. Okay, polar molecules have those permanent dipoles or their dipole moments. And because of that, they don't have to form instantaneous ones. They're stronger. Okay, also remember, even dipole-dipole forces or polar molecules have those LDFs as well. Everything has LDFs. So here, this is polar, and it is polar because it has different outside atoms. And so the carbon side is the partial positive side. The oxygen is partial negative because remember our electronegativity goes like this. Oxygen's more electronegative than carbon. So they're attracted to one another by their partial charges between different molecules. Again, remember, intermolecular forces are between molecules, not in the molecule. So here are 2 examples. So this one is polar. This one is nonpolar. Notice the boiling point is higher, the melting point is higher of the polar molecule because it has, excuse me, dipole-dipole. And it has LDF. So that is for the polar molecule. So polar liquids are miscible. This means they mix with other polar liquids, but they are not miscible, or we would say immiscible, with nonpolar liquids. So with this, it's likes dissolve likes. If it is polar in a polar liquid, it will dissolve. If it is nonpolar in a nonpolar liquid, it will dissolve. If it is polar and nonpolar, it will not dissolve. They have to be the same polarity to be able to be miscible. So here are some examples. We've got pentane and water. We've got oil and water in the ocean. And then we have oil and vinegar. All of those are immiscible or not miscible. Okay, so to determine if it has dipole-dipole forces, you need to determine if it's polar. If it's polar, it has dipole-dipole forces. If it is not polar, it only has LDF. Okay, this is, use your polarity rules from before. Lone pairs on center is polar or different outside atoms. All right, so to determine if it's polar or not, you have to draw them. So A is carbon dioxide. It looks like this. There are no lone pairs on the center, so this is nonpolar. B is CH2. I did draw one of these. Cl2. This is polar because it's got different outside atoms. Again, remember, if they have different outside atoms, regardless of how many, they are polar. Okay, this is nonpolar. I'm going to write MP. So it wants to know which one has dipole-dipole forces. B has dipole-dipole forces. I didn't realize I cut that off. Okay, because it's polar. You're just looking for polarity. You don't have to do all these arrow things. Okay, so this one is nonpolar. Normally you have to draw them. Remember, carbon only gets 4 bonds, which means it has no lone pairs. This one is polar. That's because it's got different outside atoms. I don't have to draw it. This one is polar. So B and C have our dipole-dipole forces. Next, strongest one is hydrogen bonding. Now, hydrogen bonding is still a type of intermolecular force, which means it is not a true bond. It is an attraction to other molecules of the same type of intermolecular force. Also, to be hydrogen bonding, they have to be polar. So it's polar with H, and H has to be attached to F, O, or N. Any of those. Those are the most electronegative elements on the periodic table. And if hydrogen is attached to one of them, it makes a hydrogen bond. Again, it must be attached. Also, these are polar, which means they also have dipole-dipole. So Here is an example. Again, the dotted line, this part here, this is the IMF, not the bond. The IMF is the dotted line. It's the attraction between the molecules. Again, here in this picture, hydrogen is directly attached to oxygen. So here we've got our hydrogen bonding. Notice our boiling point is now on the positive 64.2. But this bottom one, this one is nonpolar, so this one only has the LDFs. But that top one has hydrogen bonding, dipole, dipole, and LDF. Here is an image of how water is attracted to each other in its hydrogen bonding. Again, remember the dotted lines are the IMFs. Okay, I know hydrogen bonding is kind of counterintuitive, like you want to say it's a bond, but it's just an intermolecular force. Notice in all of these setups, the positive part is attracted to the negative. The positive is attracted to the negative. They have to be opposites attract. So, one of these is liquid at room temperature. Which one and why? Remember that liquid has moderate intermolecular forces, solids have the most, and gases have the least. That was from last class. So here, because we've got different outside atoms, this one's strongest is dipole-dipole. But remember, it also has LDF. This one's strongest is also dipole-dipole because of this F here. But here we've got that O attached to an H. This makes it hydrogen bonding. Because of that, the hydrogen peroxide is strongest. So this one will be our liquid at room temperature because it has the strongest intermolecular forces. Okay, between these two, we're looking at which one has higher boiling point. So they are both polar. You're looking for one that has hydrogen bonding, HF, because it's F, O, and N that have to be attached. So HF has hydrogen bonding, which is the strongest intermolecular force. Therefore, it has the higher boiling point. Okay, ion dipole forces we're going to visit in chapter 13, so I generally don't test them too much now. Right now, what you need to know is that the negative oxygen side is attracted to the positive in a cation, and the positive hydrogen side is attracted to the negative in an anion. And the water molecules will orient themselves so they are in this opposites attract situation. That's what you need to know for now. All right, this is the strength. Okay, again, we'll talk about ion dipoles later. So dispersion forces are the weakest. They're in everything. Dipole are moderate. They are stronger. They're only in polar molecules. And then hydrogen bonding is the strongest. There are hydrogen attached to F, O, or N. If you have hydrogen bonding, that also means you have dipole, and LDF. If you have dipole, you also have LDF. Okay, ion dipole is different. It's its own thing where it's compounds and polar molecules. All right, so this is just talking about DNA is held together by hydrogen bonding. You should have seen that. And notice they are dotted lines. They show them as dotted lines. So these are our H bonds, which are our intermolecular forces. That is physically what holds the structure together, is that the hydrogen bonding is attracting the molecules to one another. All right, that's it for today. Y'all have a great day.